In probability theory, the expected value of a random variable is intuitively the long-run average value of repetitions of the experiment it represents. For example, the expected value of a six-sided die roll is 3.5 because, roughly speaking, the average of an extremely large number of die rolls is practically always nearly equal to 3.5, less roughly. The law of large numbers guarantees that the arithmetic mean of the values almost surely converges to the expected value as the number of repetitions goes to infinity. The expected value is also known as the expectation, mathematical expectation, average, mean value, mean, or first moment. More practically, the expected value of a discrete random variable is the probability-weighted average of all possible values. In other words, each possible value the random variable can assume is multiplied by its probability of occurring, and the resulting products are summed to produce the expected value. The same works for continuous random variables, except the sum is replaced by an integral and the probabilities by probability densities. The formal definition subsumes both of these and also works for distributions which are neither discrete nor continuous. The expected value of a random variable is the integral of the random variable with respect to its probability measure. The expected value does not exist for random variables having some distributions with large tails, such as the Cauchy distribution. For random variables such as these, the long tails of the distribution prevent the sum integral from converging. The expected value is a key aspect of how one characterizes a probability distribution. It is one type of location parameter. By contrast, the variance is a measure of dispersion of the possible values of the random variable around the expected value. The variance itself is defined in terms of two expectations. It is the expected value of the squared deviation of the variable's value from the variable's expected value. The expected value plays important roles in a variety of contexts. In regression analysis, one desires a formula in terms of observed data that will give a good estimate of the parameter giving the effect of some explanatory variable upon a dependent variable. The formula will give different estimates using different samples of data, so the estimate it gives is itself a random variable. A formula is typically considered good in this context if it is an unbiased estimator, that is, if the expected value of the estimate can be shown to equal the true value of the desired parameter. In decision theory, and in particular in choice under uncertainty, an agent is described as making an optimal choice in the context of incomplete information. For risk-neutral agents, the choice involves using the expected values of uncertain quantities, while for risk-averse agents it involves maximizing the expected value of some objective function, such as a von Neumann-Morgenstern utility function. One example of using expected value in reaching optimal decisions is the Gordon-Loeb model of information security investment. According to the model, one can conclude that the amount a firm spends to protect information should generally be only a small fraction of the expected loss. Definition: univariate discrete random variable, finite case. Suppose random variable x can take value x1 with probability p1, value x2 with probability p2, and so on, up to value xk with probability pk. Then the expectation of this random variable x is defined as since all probabilities pi add up to 1. The expected value can be viewed as the weighted average, with pi's being the weights. If all outcomes xi are equally likely, then the weighted average turns into the simple average. This is intuitive. The expected value of a random variable is the average of all values it can take, thus the expected value is what one expects to happen on average. If the outcomes xi are not equally probable, then the simple average must be replaced with the weighted average, which takes into account the fact that some outcomes are more likely than the others. The intuition, however, remains the same. The expected value of x is what one expects to happen on average. Example 1. Let x represent the outcome of a roll of a fair six-sided die. More specifically, x will be the number of pips showing on the top face of the die after the toss. The possible values for x are 1, 2, 3, 4, 5, and 6, all equally likely. The expectation of x is if one rolls the die n times and computes the average of the results, then as n grows, the average will almost surely converge to the expected value, a fact known as the strong law of large numbers. One example sequence of 10 rolls of the die is 2, 3, 1, 2, 5, 6, 2, 2, 2, 6, which has the average of 3.1. With the distance of 0.4 from the expected value of 3.5, the convergence is relatively slow. The probability that the average falls within the range 3.5 plus or minus 0.1 is 21.6% for 10 rolls, 46.1% for 100 rolls, and 93.7% for 1,000 rolls. See the figure for an illustration of the averages of longer sequences of rolls of the die and how they converge to the expected value of 3.5. More generally, the rate of convergence can be roughly quantified by e.g. Chebyshev's inequality and the Variance theorem. Example 2. The roulette game consists of a small ball and a wheel with 38 numbered pockets around the edge. As the wheel is spun, the ball bounces around randomly until it settles down in one of the pockets. Suppose random variable x represents the outcome of a $1 bet on a single number. If the bet wins, the payoff is $35, otherwise the player loses the bet. The expected profit from such a bet will be i.e. the bet of $1 stands to lose $0.0526, so its expected value is $0.9474. Univariate discrete random variable. Countable case. Let x be a discrete random variable taking values x1, x2, with probabilities p1, p2, respectively. Then the expected value of this random variable is the infinite sum provided that this series converges absolutely. If this series does not converge absolutely, we say that the expected value of x does not exist. For example, suppose random variable x takes values 1, -2, 3, -4, with respective probabilities c12, c22, c32, c42. Where c equals 6, pi2 is a normalizing constant that ensures the probabilities sum up to 1. Then the infinite sum converges and its sum is equal to lane 0.69315. However, it would be incorrect to claim that the expected value of x is equal to this number. In fact, x does not exist, as this series does not converge absolutely. Univariate continuous random variable. If the probability distribution of admits a probability density function, then the expected value can be computed as general definition in general. If x is a random variable defined on a probability space, then the expected value of x, denoted by x or ex, is defined as the Lebesgue integral. When this integral exists, it is defined as the expectation of x. Not all random variables have a finite expected value, since the integral may not converge absolutely. Furthermore, for some it is not defined at all. Two variables with the same probability distribution will have the same expected value. If it is defined, it follows directly from the discrete case definition that if x is a constant random variable, i.e., x equals b for some fixed real number b, then the expected value of x is also b. The expected value of a measurable function of x, g, given that x has a probability density function f, is given by the inner products of f and g. This is sometimes called the law of the unconscious statistician. Using representations as Riemann's Dieltjes integral and integration by parts, the formula can be restated as is a special case. Let alpha denote a positive real number. Then in particular, if alpha equals 1 and PR x0 equals 1, then this reduces to where f is the cumulative distribution function of x. This last identity is an instance of what, in a non-probabilistic setting, has been called the layer cake representation. The law of the unconscious statistician applies also to a measurable function g of several random variables x1, xn having a joint density f. Properties. Constants. The expected value of a constant is equal to the constant itself, i.e., if is a constant, then monotonicity if in a random variable such that almost surely, then linearity. The expected value operator is linear in the sense that the second result is valid even if is not statistically independent. If, combining the results from previous three equations, we can see that for any two random variables and any real numbers a, b and c. Iterated expectation. Iterated expectation for discrete random variables. For any two discrete random variables, one may define the conditional expectation, which means that e x y equals y is a function of y. Let g be that function of y, then the notation e x y is then a random variable in its own right, equal to g. Lemma. Then the expectation of x satisfies. Proof. The left-hand side of this equation is referred to as the iterated expectation. The equation is sometimes called the Tower rule or the Tower property. It is treated under law of total expectation. Iterated expectation for continuous random variables. In the continuous case, the results are completely analogous. The definition of conditional expectation would use inequalities, density functions, and integrals to replace equalities, mass functions, and summations, respectively. However, the main result still holds. If xy, then e x e y. In particular, if we set y to x, we know xy and minus xy. Therefore, we know e x e y and e minus x e y. From the linearity of expectation we know minus e x e y. Therefore, the absolute value of expectation of a random variable is less than or equal to the expectation of its absolute value. This is a special case of Jensen's inequality. Non-multiplicative Atty. If one considers the joint probability density function of x and y, say j, then the expectation of xy is in general. The expected value operator is not multiplicative, i.e., e x y is not necessarily equal to e x e y. In fact, the amount by which multiplicativity fails is called the covariance. Thus multiplicativity holds precisely when cov equals 0, in which case x and y are said to be uncorrelated. Now if x and y are independent, then by definition j equals fg, where f and g are the marginal PDFs for x and y. Then uncov equals 0. Observe that independence of x and y is required only to write j equals fg, and this is required to establish the second equality above. The third equality follows from a basic application of the Fubini-Tonelli theorem. Functional non-invariance in general, with the exception of linear functions. The expectation operator and functions of random variables do not commute. That is a notable inequality concerning this topic is Jensen's inequality, involving expected values of convex functions. Relation to characteristic function. The probability density function of a scalar random variable x is related to its characteristic function phi x by the inversion formula. We can use this inversion formula in expected value of a function g to obtain changing the order of integration. We get whereas the Fourier transform of this can also be seen as a direct consequence of Plancherel theorem. Uses and applications. It is possible to construct an expected value equal to the probability of an event by taking the expectation of an indicator function that is 1 if the event has occurred and 0 otherwise. This relationship can be used to translate properties of expected values into properties of probabilities, e.g., using the law of large numbers to justify estimating probabilities by frequencies. The expected values of the powers of x are called the moments of x. The moments about the mean of x are expected values of powers of x minus e x. The moments of some random variables can be used to specify their distributions, via their moment-generating functions, to empirically estimate the expected value of a random variable. One repeatedly measures observations of the variable and computes the arithmetic mean of the results. If the expected value exists, this procedure estimates the true expected value in an unbiased manner and has the property of minimizing the sum of the squares of the residuals. The law of large numbers demonstrates that, as the size of the sample gets larger, the variance of this estimate gets smaller. This property is often exploited in a wide variety of applications, including general problems of statistical estimation and machine learning, to estimate quantities of interest via Monte Carlo methods. Since most quantities of interest can be written in terms of expectation, e.g., whereas the indicator function for set, i.e., in classical mechanics, the center of mass is an analogous concept to expectation. For example, suppose x is a discrete random variable with values xi and corresponding probabilities pi. Now consider a weightless rod on which are placed weights, at locations xi along the rod and having masses pi. The point at which the rod balances is e x. Expected values can also be used to compute the variance by means of the computational formula for the variance. A very important application of the expectation value is in the field of quantum mechanics. The expectation value of a quantum mechanical operator operating on a quantum state vector is written as the uncertainty and can be calculated using the formula expectation of matrices. If X is an m times on matrix, then the expected value of the matrix is defined as the matrix of expected values. This is utilized in covariance matrices. Formulas for special cases. Discrete distribution taking only non-negative integer values when a random variable takes only values in 0, 1, 2, 3. We can use the following formula for computing its expectation. Proof. Interchanging the order of summation, we have this result can be a useful computational shortcut. For example, suppose we toss a coin where the probability of heads is p. How many tosses can we expect until the first heads? Let x be this number. We are counting only the tails and not the heads, which ends the experiment. In particular, we can have x equals 0. The expectation of x may be computed by. This is because, when the first I tosses yield tails, the number of tosses is at least I. The last equality used the formula for a geometric progression, where continuous distribution taking non-negative values analogously with the discrete case above. When a continuous random variable x takes only non-negative values, we can use the following formula for computing its expectation. Proof. It is first assumed that x has a density fx. We present two techniques, using integration by parts, and the bracket vanishes because as using an interchange in order of integration.